Yeah, David, if you want to come up, and Jerry. So as they're getting set up, thank you and welcome to the uses of the Pacific Wave International Exchange in Climate Research panel. And I appreciate a couple people. David got kind of thrown into this. We are bringing a couple of our people in on Zoom, so hopefully they're going to be able to participate that way. As Lewis said, I'm Marla Meehl. I work at the National Center for Atmospheric Research in Boulder, Colorado, and I manage the networking for NCAR and UCAR, but I also do manage the Front Range Gigapop, which is a very small version of CENIC in Colorado and Wyoming. We partner very closely with CENIC on the Western Regional Network, the Pacific Research Platform, Pacific Wave, and the National Research Platform. And I am very excited to introduce this panel of experts on Pacific networking and climate research and its impacts on the Pacific Islands. I suggested this panel because I thought it would be interesting to hear a case study of how powerful and evolving networks in the Pacific and that CENIC and the University of Hawaii and its partners have developed and managed are used to enable and further scientific research. So without further ado, our panel consists of Dr. David Lassner, which you just got quite an explanation on, President of the University of Hawaii, and he'll be talking about Hawaii's Pacific Island Research and Education Network, PIREN. Dr. Gerald Meehl, the name is not coincidental. Jerry is my husband, and I'm very proud of him, and I appreciate him agreeing to do this. He got kind of roped in. He's going to be talking about climate change in the Pacific region, the physical setting. Dr. Kristie Ebi from the University of Washington will be talking about health risks of climate change in the Pacific Islands. And Dr. Victoria Keener from the East-West Center, which was mentioned earlier, at the University of Hawaii, will be talking about climate change, human migration, and health in the Republic Islands of Marshall Islands. So, thank you all. David, you want to start us off?
Oh, cool. So I'm doing mostly infrastructure, and I'm going to pull out a watch, so I'm really on time. Poor Marla. I told her I was going to go for about 30 minutes. That's the hokulea, the canoe that Lewis mentioned. So let me just say a word. I always want to remind people of Hawaii's proud history. The Aloha Protocols, any of you who are engineering students, developed by Norm Abramson and his team at the University of Hawaii. He went to UH as a grad student to surf. The PACOM project, some of you will remember, was the early project Dr. Torben Nielsen in our computer science department put in literally the first IP connections into Australia, New Zealand, Japan, Korea, before the internet was commercialized at all. And then, as far as I know, I've just kind of been trying to nose around about this. The University of Hawaii was actually the first U.S. research and education institution to start discovering that you could buy these things called IRUs if you didn't want to pay monthly or annual fees for circuits. So this is, I'm going to flash through a couple of these quickly. This is the Internet 2 set of international partners. Note, nothing in the Pacific. This is the APAN, the Asia Pacific Advanced Networks, the multinational R&E networking entity region. You'll note no nodes in the Pacific other than Hawaii. Here's the famous glyph. Now, this is the old one. I'll update it in a moment. But again, you will see nothing in the Pacific other than Hawaii. So this is the reality in the part of the world where I am. We have seen research and education networks, and you all know what they are and why we build them, throughout the world, and many people in this room have been quite instrumental in developing these in Africa, Central America, Latin America, Southeast Asia, and other parts that have traditionally been underserved. And so one of my passions became, how can we get the Pacific engaged in this? So this gives you an idea of what the region looks like. It is huge relative to almost any other part of the world, very sparsely populated. If you leave out Papua New Guinea, which I think is over 6 million people, the total population of this region is under 3 million, and that the largest after Papua New Guinea would be Fiji with around 800,000. Some of these islands are sovereign and have less than 10,000 population. So you sort of picture the economics of that, and it gives really new meaning to the challenges of rural connectivity. A number of people have tried to get engaged in this over many years. The EU, George McLaughlin and Denny Vendrome. We had a small eager grant from NSF to help us think about how feasible this was going to be. And I'll say a word about our current project, Pyron, in a moment. And I do want to mention we're trying to work closely with other countries, developed countries that are interested in making investments. So the challenges are different, and I won't go through all of these, but these tend to be developing countries with strong governmental control. There is not competitive access to fiber, and even if you can buy capacity, there are all kinds of issues around interconnect. There tend not to be exchanges at all, so it is very common for packets to travel thousands of miles to get between two locations on the same island if the competitive partners aren't working together. This is something that many of us in the U.S. discovered 20 plus years ago, and it is still being rediscovered, but it is particularly a challenge for island nations at the end of very skinny links that are also quite expensive. So this is the newest glyph map, and Lewis mentioned this project, and we're pretty excited. It's hard to see. You can kind of make out Hawaii as the thing kind of next to Central America if you look to your left, and then to the left farther along is Guam. So Guam turns out to be really interesting, and I'm one of those people who I used to spend more time than I do now staring at maps of fiber. Guam has an incredible amount of fiber passing through it, but it was pretty much touching at a shore and then maybe interconnecting with another fiber system and moving on. But almost no packets were exchanged there, only light. And we started working together, and Steve Huter somewhere around, to work with the University of Guam in particular and some of the telecom providers to try to develop, let me come back to it, an open exchange for R&E. And we just got that thing up and running with a 100 gigabit link from Guam to Hawaii, and we're developing that on. So that's the beginning of breaking through into the Pacific itself. And again, I won't go through these, and Vint had commented on this as well, and I also would have lost this bet. As recently as 3 or 4 years ago, the only places that had really active fiber were Fiji and Guam. And again, as I mentioned, Guam wasn't really taking advantage of it for R&E. It was really it was like an airport full of people making stopovers and catching their next plane. French Polynesia came on board with a system that connects them to Hawaii and about 5 of their islands. And since then, if you look over on the right, you begin to see especially a number of new regional projects. These are mostly being supported by the World Bank and the Asian Development Bank. There seems to be a real possibility that by 2020, every one of those, the dots, meaning the government or the economy, will at least have one connection. Now, if you take, some of these places have 50 plus populated islands, so you don't solve the problem when you get to one island in Fiji, but you begin to crack at the problem, and it tends to be the most populated place. And sometimes there are other opportunities either for domestic fiber systems, wireless systems, and there's still a lot of satellite in use there. It's pretty amazing. The one place that nobody is talking about yet is Pitcairn Island. Population is about 50, I think. And these are the kinds of pictures people in the Pacific are starting to develop as they think about intra-Pacific connectivity rather than just focusing on connecting to typically Australia, Hawaii, the West Coast. They're now looking at how do they connect to each other as well, which is really amazing. And without going into the, where the Hokulea is going next, it looks like it will be a circumnavigate the Pacific counterclockwise from Alaska, again, visiting primarily with indigenous or First Nations people in each of the regions around the whole Pacific Rim, including Asia. So I want to have a special shout out to one of our partners. The University of South Pacific is a really unique institution. It is a regional university that is owned and operated by 12 different countries based in Fiji. But it is not purely a Fijian institution. They've been engaged in distance learning for decades. This is their current satellite network, and they have educational institutions. When we're looking for R&E partners, very often we're looking to the USP campus in that particular nation or location. And thanks to CENIC and NSRC, Steve Huter, for sponsoring. Edwin is somewhere in this room from USP. Say hello if you get a chance. We're really focused on building capacity there as a means of outreach into the region. This is our NSF project. It's one of the international research networking projects from the NSF. It's in production networking, so that's our job, is to deploy production networks. We work a lot with Australia, New Zealand, and this little side project to try and extend R&E networking into the Pacific region. Lewis already showed this. This is the aspirational view, showing where fiber is and will be throughout the Pacific, and architecturally how we can get most of these places connected to Guam, Hawaii, Fiji, which are the current hubs. Samoa is really actively pursuing the opportunity to become a hub in its part of the Pacific. It's a little bit east of Fiji and presents an opportunity, and they've got 2 major projects going in there as well. This is the Guam Open Exchange. I think Lewis meant to show a picture but didn't get there. So it's a regional hub, both for a number of locations in the North Pacific or Western Pacific, but interestingly, it is also extremely well connected into Asia, Southeast Asia, and the U.S. So I'm going to zip through. I want to show this picture because, and Vint talked about people-centered networking, and this is something that NSRC does, one of our partners. We cannot deploy these networks without building the human capacity. And this is where the collaborations with colleges and universities in the region really helps us as we're going out to the R&E partners. And I'll just zip because Marla would shoot me if I didn't show a picture of Mauna Loa. But from a climate change perspective, this is the site. That graph you see on the left is the Keeling curve, which is the longest running study of greenhouse gases in the atmosphere. And you can sort of see that this is a long-term, even if it wavers up and down, it is going up. And I'll just quickly, because others on the panel will talk about the science, these are some of the projects going on. This is the Pacific Integrated Ocean Observing System based at University of Hawaii. This is a Pacific Islands Climate Studies involving Hawaii, Guam, and others in the Pacific. Some of our work with sensors in the Pacific and collaboration, and you can see the looks in these places are very different than what we're accustomed to. But a big part of this is really engaging with the people of the Pacific, hearing their stories and their challenges as we attempt to understand what they're being faced with climate change and how they, of course, have done nothing to create climate change in their nations, but they are, as I know others will comment, they are faced with these challenges as the low-lying atolls face sea level rise, that entire islands almost certainly will disappear. In closing, mahalo.
So Marla says she's going to be a really tough moderator, And if I get to 15 minutes, she's going to cut me off. So the pressure's on here. So, good. Okay, so if you say Pacific climate to somebody in California or somebody in the Pacific region, they usually think El Nino. And they think of El Nino as this kind of wrathful monster that's wreaking havoc on human societies and ecosystems. But El Nino events are the largest source of year-to-year climate variability in the Pacific region. They're naturally occurring. They occur about once every 3 to 5 years. They usually last about a year. They usually start in Northern Hemisphere spring and end the following Northern Hemisphere spring. So they you refer to an El Nino event usually as a 2-year event. And the most recent event we had was the 2015-2016 El Nino. It started in the spring of 2015 and more or less ended in the spring of 2016. And this is kind of what an El Nino looks like. This is what the 2015-2016 El Nino looks like. And this is just ocean surface temperatures, departures from normal. And you can see this huge patch of red and orange in the eastern tropical Pacific. That's the El Nino event. It's a patch of warm water that's warmer than normal by about 4 degrees centigrade. It covers about twice the size of the continental U.S., so it's a huge patch of unusually warm water. And you think, well, that's only 3 or 4 degrees, but just that small increase of ocean temperatures can shift precipitation patterns around in the Pacific and actually affect the track storms take over the U.S. There's a lot of impacts associated with El Nino events, and the 2015-2016 event was no different. You can see in the central Pacific there where the water was warmer, you get wetter conditions. Those are the purple colors. And it's drier and hotter than normal in the western Pacific over Southeast Asia and South Asia. So this is a fairly typical El Nino event. It also produced wetter conditions in the southern tier states and in parts of California. The flip side of El Nino is La Nina. These are also events that occur naturally. They're about every 3 to 5 years in frequency. They also last about a year. We're currently in a weak La Nina event. You can see those kind of blue temperatures there in the eastern equatorial Pacific. Temperatures right now are below normal by a couple of degrees centigrade. And the impacts from a La Nina event are exactly the opposite as to what they are during an El Nino. So over the cooler water in the Pacific there, you see dry conditions. It's wetter and cooler over in the western Pacific and dry in the southwestern U.S. and parts of California that you're very familiar with recently. So everybody wants to know, what's the future going to happen? What's going to happen with El Nino in the future? As the average temperatures warm up in the Pacific, the impacts of El Nino events are going to continue to occur. Still going to have El Nino and La Nina events. They're going to be occurring on a ever-warming base state, so the impacts are going to be more severe. So areas that are now hot and dry in the western Pacific during present-day El Nino events will be hotter and drier in future El Nino events. But another more menacing impact from El Nino events is coral reef bleaching. This is a relatively new problem. We saw the first large coral reef bleaching event in the 1982-83 El Nino, and coral is very interesting. Coral is not one organism, it's actually two. It's the coral organism that provides the skeleton and the zooxanthellae algae that provide the color. The algae live on top of the coral skeleton and through photosynthesis provide nutrients to the coral, and that's how the organisms live in this symbiotic relationship and survive. On the left is a healthy coral reef there that has a lot of color to it from the algae. Coral are adapted to a certain temperature range in the ocean, and if the temperatures rise above a certain threshold, the coral freaks out, kicks out the algae, and that means the color leaves because the algae's gone, and all that's left is the white calcium carbonate coral skeletons, and that's a coral reef bleaching. And so we just came through the largest coral reef bleaching event in recorded history. Started in late 2014, ended last year. Reefs bleached all over the world. This is an example of a reef bleaching in Pago Pago in American Samoa. There in the upper left part of the panel, you can see the healthy reef. The right part of the panel is the bleached reef. There was reefs bleached all around Hawaii. And you say, well, okay, does bleaching kill coral reefs? And some reefs that bleach do recover. Somehow the algae come back and they reform and the reef survives. But usually mortality can reach up to 50% in a reef that's bleached. This is an example of a reef, again, in Pago Pago in American Samoa. Healthy reef on the left, bleached reef in the middle. By August 2015, it was dead. So this was a huge event. Reefs bleached all over the Pacific. These red dots are reefs that bleached in the Pacific, and you can see reefs in the Indian Ocean bleached as well as in the Atlantic. The Great Barrier Reef off Australia was particularly hard hit. They think that about 70% of the Great Barrier Reef bleached in this last event. This is an aerial shot of just some of the reef structures there, and you can see all the white blotches as the bleached coral. And they think that maybe as much as 50% of the Great Barrier Reef may not survive this most recent event. There's a great video there that you can watch that shows this Chasing Coral, which is a really great film documenting that event. So what's going on? So this is a time evolution of tropical Pacific Ocean temperatures. The spikes that are going up are the El Nino events. The spikes that are going down are the La Nina events. The lower blue line is the trend line, and you can see that over this time period from 1950 to present, average ocean temperatures in the Pacific have warmed up about 1 degree centigrade. But you can also see that the upper blue line there is kind of a trend line for these very large El Nino events. And you can see that the first mass reef bleaching event was 82-83. Coral reef biologists had never seen anything like this before. They'd seen local bleaching, but nothing of this magnitude. That was exceeded by the 97-98 El Nino event. That was the record El Nino and record reef bleaching event, which was exceeded by the 2015-2016 El Nino, which is now the record holder for the largest mass coral reef bleaching event in history. And it also extended into the non-El Nino year of 2017, which is somewhat worrying. Survivability of coral reefs is now in question. That it's really unclear if coral reefs can survive even for the next 50 years or so. Another threat to coral reefs and marine organisms is ocean acidification. This is a simple chemistry problem. As you burn fossil fuels, you put CO2 in the atmosphere. Some of the CO2 goes into the ocean. The CO2 reacts with the water molecules. H2O forms carbonic acid. The carbonic acid reacts with calcium carbonate skeletons in coral organisms and marine vertebrates and breaks those down. So that's another threat to marine life in the Pacific. People want to know, what about tropical cyclones, typhoons, and hurricanes? Those are three names for the same storm. So same storm, different basins. We call them hurricanes in the Atlantic, typhoons in the Western Pacific, tropical cyclones in the South Pacific and Indian Ocean. The top map shows observed tropical cyclone and typhoon tracks in the various basins over a 10-year period. The middle panel is a simulation from a climate model showing that it has a capability of simulating tropical cyclone tracks over most of these regions. The bottom panel is the same model that's been run forward in time with increasing carbon dioxide. And just by eye, you can see, comparing the bottom panel with the middle panel, there's fewer tracks in the bottom panel. The result of this and other studies have indicated that it's likely we'll have fewer tropical cyclones, typhoons, and hurricanes in the future, but the ones that form will be more intense. Sea level rise is a big deal in the Pacific. And you can get sea level rise happening for two reasons. One is just simple physics. As you warm water, it expands. So if you warm the upper layer of the ocean, it expands, and that raises sea level. That's called thermal expansion. The other source is if you have ice that's locking up water on land, and if you melt some of that ice on land and it goes into the ocean, the water goes into the ocean, that adds mass to the ocean, that also raises sea level. Sea ice, you've been heard about sea ice shrinking in the Arctic. Sea ice forms seasonally on the water that's already in the ocean, so that's not adding any mass to the ocean. It's the ice that's on land that melts and adds water to the ocean that adds to sea level rise. So if you're living on Tetiaroa Atoll, formerly owned by Marla and Brandu and French Polynesia, and the highest point of land is 6 feet above sea level, you've got to worry about things that are happening thousands of miles away in Antarctica and Greenland. In the Pacific, we're already seeing effects of the sea level rise that's already occurred. Sea level rise has risen about 8 inches over the last 50 years, and these inundation events are seen most frequently when you have naturally occurring high tides. So if you have a high tide, it's occurring on top of an average sea level rise that's already occurred, and you get greater coastal inundation. These are some examples from some atolls in the Pacific. So we're not worried about the entire Greenland ice sheet or the entire Antarctic ice sheet melting. We're worried about the rate that it's melting. So the two questions we ask about sea level rise is how much will melt and how fast. Okay, how much and how fast. Those are the big questions. The ice sheets work in the kind of similar way. Snow accumulates, forms ice, forms this big volume of ice. It's heavy, it presses down, pushes out the ice at the edges. In Greenland, it pushes out these big outlet glaciers into the ocean. They calve into the ocean. The concern is that as the ocean warms up, you're going to be able to melt more ice on the face of these outlet glaciers, get more calving, more ice comes out, and you increase the rate into the ocean. Antarctica is a little bit different. They have these ice shelves. Ice shelves are where the ice sheet feeds the ice into the ice shelves that are floating on ocean. So you have melting at the face of the ice shelves that can increase calving. You can also get warmer water getting underneath the ice shelf and melt it from underneath. We've already seen a fairly rapid disintegration of a couple ice shelves in Antarctica so far. And the idea is that when you disintegrate an ice shelf, the ice shelf is kind of holding back the ice that's trying to come out into the ocean from the ice sheet, and you accelerate ice flow into the ocean from that. So the projections are pretty uncertain because the people that study ice sheets are seeing things they've never observed before. We're now living in an era that's warmer than any time period in human history, and so the ice sheets are doing things they've never seen before. So they're trying to figure out what the processes are, how stable they are, how they can become unstable, to answer this how much and how fast question. Projections are, you see, by 2100, estimates are maybe around 3 feet of sea level rise with big error bars. See, the shading is uncertain. As we go into the future, the uncertainty increases. This is a big, compelling science question right now. The other kind of ominous thing about Antarctica, which is interesting, is that a lot of the Antarctic continent is below sea level. You have 2 miles of ice. It's very heavy. It's pushed down the crust. It's pushed down the continental mass. And so you can see the green parts there are areas of the continent of Antarctica underneath the ice that's above sea level. The light blue is areas that are below sea level. So a lot of Antarctica is below sea level. And if you imagine water trying to get underneath that ice sheet and destabilizing from underneath, you can actually float bigger parts of the ice and disintegrate it more quickly. So how do we study this? How do we get a handle on this? What we do is we have numerical representations of the Earth system. We have components of atmosphere, ocean, land surface processes, sea ice. We have ice sheet models for the first time in this current generation of Earth system models we're running to get at sea level rise, ocean biogeochemistry to look at ocean acidification, atmospheric chemistry to look at air pollution. And we, in the upper right, we try to represent this numerically with some kind of a grid. This is a simple latitude-longitude grid. At each grid point, at each intersection of a latitude and longitude line, at each grid point, we solve these equations from physics and thermodynamics, many levels in the atmosphere, many layers down deep in the ocean, over the land surface, sea ice, etc. And we try to simulate something that looks like what's in the lower left there. For the Pacific, the features we're trying to simulate, you can see kind of south of North America, that kind of line of big thunderstorms that's going across there about 5 degrees north latitude. It's called the Intertropical Convergence Zone. That's where the trade winds converge from the northern and southern hemisphere and push up the air and form these big thunderstorms. And a lot of times you get tropical cyclones that spawn out of the ITCZ. And that's moving with the trade winds from east to west. In the mid-latitudes, you get the big low-pressure centers, the big storms with the big cold fronts that come arcing out into the all the way down into the tropics sometimes. Those are going from west to east. And you can see this particular picture was when Hurricane Katrina was hitting New Orleans, so we wanted to be able to simulate tropical cyclones and hurricanes as well. This is an animation from one of our Earth system models at NCAR. I'm just going to try to run this, and you can see in the left there, you can see the ITCZ, and you can see this is northern summer, so you see some hurricanes spawning and spinning off in south of Hawaii. You see a typhoon there off of Asia hitting Japan. There's another typhoon that's forming. It's going to come up and hit China. You can see a lot of precipitation over India. That's the Indian monsoon. You can see the mid-latitude storms going along from west to east in the mid-latitudes with these big cold fronts that come all the way down into the tropics. So this is, to me, is amazing. So with equations, we're able to simulate this level of complexity in the Earth system. So we have tools that we can actually try to address and quantify these risks to the system. Now this is where the networking comes in, because what we've done is we've tried to coordinate efforts across the groups around the world who do this kind of Earth system modeling. There's currently 33 modeling groups that do this kind of high-end Earth system modeling in 16 countries. And we've tried to coordinate experimentation across all these groups so everybody's running the same experiments. And if everybody's running the same experiments, you can compare the results and try to quantify uncertainty a little bit better. And we think that this current phase of what's called the Coupled Modeling or Comparison Project, CMIP6, is going to generate about 10 petabytes of model data. So how do you get at this data? So starting on the left-hand side, the modeling groups run all these experiments. They put these experiments on a local server. It's connected to the Earth System Grid Federation. And so somebody who has a laptop that's maybe and an internet connection that's maybe sitting in Guam or Hawaii or California or somewhere else can go through a web portal and access current state-of-the-art Earth system model output and try to understand better climate variability and climate change. So summary is these future threats to the physical system are warming ocean temperatures obviously will cause a lot of problems, already are causing problems. We get more intense El Nino impacts. This includes droughts, floods, extreme heat, and coral bleaching. Ocean acidification is just a product of the chemistry of increased CO2 in the air that causes problems with ocean marine organisms. It looks like there will be fewer tropical cyclones or typhoons, but the ones that form will be more intense. Sea level rise is a big issue, but there's a lot of uncertainty depending on how stable the ice sheets are and how fast they may disintegrate, to answer the how much and how fast questions. And we use Earth system models to try to quantify these risks, and of course these produce huge data volumes, and we're doing this distributed archival and analysis over the Earth System Grid Federation with access web portals through the internet. Thanks.
All right, Dr. Ebi, are you there?
I am. And who's going to handle the slides?
I guess I can.
Oh, good.
Or are you driving remotely? I'm looking at our AV people back in the back. Why don't I go ahead and drive?
That's great. Well, thank you very much for inviting me. And it's been fascinating listening to what's gone on for the little bit before I joined. Well, a little bit that happened before the panel started. As a beginning comment, I'm supposed to talk about part of what Jerry just talked about in terms of what it means for our health. It always impresses me the just amazing research that Jerry and others have done to give us insights into how climate change will be changing weather patterns around the world. One thing that struck me in the last couple of slides is the level of investment in the consequences, potential consequences for human and natural systems is incredibly modest compared with what's been invested in the climate models. We understand in health systems quite a bit about how weather and climate affect our health, but the extent of investment for understanding the specifics of how climate change could alter the number of cases of climate-sensitive health outcome has been tiny. As an example, the National Institutes of Health budget on understanding climate change and health is less than 0.02% of their budget. But it's not all bad news. If we go to the next slide. The World Health Organization last summer elected a new Director General, Dr. Tedros. Depending on which document you read, Dr. Tedros either has 4 or 5 priorities for his tenure at the World Health Organization, and one of them is climate change. There has been 20 years of efforts in the Pacific and other regions to better understand what climate change could mean for our health. With Dr. Tedros in charge of WHO, we're hoping that there'll be a significant ramp up. Dr. Tedros and others at the United Nations Framework Convention on Climate Change meeting in December announced a new initiative on looking at climate change and health, specifically in the small island developing states. Next slide. So why are we concerned about climate change? As you heard from Jerry, we know that climate change is altering temperature, rainfall, the frequency and intensity of extreme events, sea level rise, ocean salinity, and the temperatures in the ocean. These in turn change exposures that are important for our health. And these change exposures either directly or indirectly then change the number of cases of climate-sensitive health outcomes. In a minute, I'll show you that with warmer temperatures, we see more diarrheal disease, for example. We know that increases in extreme events increase traumatic injuries and deaths. A big concern around the world and in the Pacific is that with warmer temperatures, more extreme events, we're seeing declines in crop yields in many places. We're also seeing declines in micronutrient content in cereal crops. This means an increase in undernutrition. So you can see there's a wide range of potential health consequences from a change in climate. All of these health consequences have other mediators, such as social political strategies, environmental measures, resilience of our health systems. So they're complicated to study. And even with that, we do have a fairly good understanding of what kinds of challenges we might face. Although, as I mentioned before, the specifics still need to be worked out with additional investment in research and in adaptation. Next slide. The overall goal is to develop a climate resilient health system. The figure on the left comes from the World Health Organization. When the World Health Organization looks at health systems, it breaks their function into 6 basic building blocks. CDC breaks these building blocks into 10. They're more or less the same, different combinations. Outside that circle, you can see then 10 areas where health systems need to work on building climate resilience, starting at the top with leadership and governance. If you go around to the left where you see service delivery in blue, you can see emergency preparedness and management. You can see climate-informed health programs and management of the environmental determinants of health. Many of the issues that Jerry touched on go directly into the challenges that are being faced in service delivery. In green on the right, there are health information systems. I've mentioned research. There's also quite interest in looking at integrated risk monitoring and early warning systems, of taking advantage of those incredibly large amounts of data that are coming from the Earth system models and understanding how we can use that to be better prepared for events when they do arise. Next slide. There was a process under the Western Pacific Regional Office of the World Health Organization to conduct what are called vulnerability and adaptation assessments in 13 countries. This is a process that's being done in all human and natural systems. Any country that has signed on to the Framework Convention on Climate Change is required to produce regular national reports. These reports include sections asking countries what are their vulnerabilities and what are their needs over the short and medium term for adapting to their vulnerabilities in the face of a changing climate. On this, you can see a long list of climate-sensitive health risks, and you can see the 13 countries across the top. As you look down that list, you'll recognize that these are most of the issues that a Ministry of Health needs to deal with. Climate change is cutting across all our health programs. So there's a lot of work that needs to be done in terms of improving how we're currently managing these health risks to take into account changes in weather patterns. You can see that all countries are worried about water security, nearly all for food security, all are worried about vector-borne diseases. That all of these issues are very important to address to make sure that we decrease our vulnerability and increase our resilience to a changing climate. Next slide. This is an example I mentioned before. This is some work that was done quite some time ago on annual average temperatures and average reporting rates for diarrheal disease across the Pacific Islands. And you can see a very clear response to average annual temperatures. As temperatures go up, pathogens replicate faster. There's also impacts of changing water availability. Jerry mentioned the El Nino events. In some of the countries in the Pacific during El Nino events, there's flooding. In others, there's drought. During flooding events, you can wash pathogens into waterways and thereby see an increase in diarrheal disease. In drought, people change how they use water in ways that actually can facilitate the transmission of diarrheal disease. So not only temperature change, but changes in the extremes also can increase diarrheal disease. Next slide. An issue of very high importance to the Pacific Islands are the non-communicable diseases, heart disease, cancer, and stroke. The prevalence of diabetes and obesity in many countries, particularly of obesity, is over 60%. prevalence of hypertension is equally as high, if not higher. This is not an area where much has been done in terms of how climate change could affect these non-communicable diseases. This is a diagram that was laid out specifically for the Pacific Islands, showing, in fact, that there are ways that a changing climate could affect how people purchase their food, what food they purchase, what food is available to purchase, how climate change then affects food security, and then the prevalence of these non-communicable diseases. Next slide, please. I wanted to spend a couple of minutes talking about a project that's ongoing right now. Well, not exactly ongoing right now. There will be a project ongoing that several of us are involved literally right now in working on a project under the Global Environment Facility, the GEF. The Global Environment Facility is the group that managed the Least Developed Country Fund, the LDCF. The Least Developed Country Fund was set up under the United Nations Framework Convention on Climate Change. There are regular calls for funding the least developed countries because, as Jerry mentioned, their emissions have been minuscule. The impacts that they're experiencing are significant and are having economic consequences, consequences for livelihoods, consequences for health. It's a two-stage process to receive funding under the Least Developed Country Fund. The first step was to write a pre-proposal, which was approved by the GEF. Full proposals are being prepared right now. We're going to have a validation workshop next week in Nandi in Fiji to pull these all together. These are for the 4 least developed countries that are in the Pacific. You can see in red the objective of the project is to enhance the capacity of national and local health system institutions, personnel, and local communities to better manage the risks of a changing climate. There's 4 main outcomes for this project. The first is around governance. This is making sure that countries update their vulnerability and adaptation assessments, develop the health component of a national adaptation plan, look at their policies and programs, and make sure that they are incorporating climate-related risks. The second is to strengthen the capacities of institutions and personnel, and this includes better managing health information, in many cases, making sure that that information is digitized, and then seeing if it's possible to develop early warning systems. The third is making sure that there's improved coverage and quality of health services, that there are health services right now that are being disrupted by heavy precipitation events, by typhoons, by a number of different activities, and finding ways to ensure that health service facilities can continue to function in a changing climate. And finally, enhance South-South cooperation through information exchange, best practice, those kinds of activities. Next slide. One of the countries involved is the Solomon Islands. There's a map on the left that shows you the Solomon Islands. You can see Guadalcanal, where the capital is located. Next slide. In 2014, in April of 2014, there was flash flooding in the capital. There had been heavy precipitation over previous days. There was certainly inadequate planning, and so flash floods occurred on the 4th of April. The figures show you the total number of cases of diarrheal disease in that year compared with other years, dengue cases, malaria cases. And so you can see at the bottom that the flooding event caused 31 deaths, 33 acute injuries, and an outbreak of diarrheal disease. About 10,000 people were displaced. So a very large impact of this event. I'm sure someone's going to ask, so in the upper right-hand corner, you can see dengue cases in 2013 were a lot higher than they were in 2014. One possible reason is that the heavy flooding washed away breeding grounds of the mosquito, Aedes aegypti, that carries dengue. Next slide. Sorry, did somebody say something?
You're at a couple minutes on your time.
Yeah, I'm close to the end. So this shows you a rotavirus disease outbreak in the Solomon Islands, also in 2014. The point of this is how this outbreak spread from one island to another. Take the next slide. This shows you the National Referral Hospital, shows you the challenges of healthcare facilities. They sit in coastal areas that are subject to flooding. In the bottom right, bottom left, you can see some of the buildings in the hospital. They're all up, they've all been elevated so the floodwaters could wash underneath them. But there's significant work that has to be done to ensure that healthcare facilities themselves continue to operate when you have extreme events. Next slide. Kiribati is another of the set of islands that are included. If you go to the next slide, this isn't specifically about health, but you can imagine what this means for health. These are projections for Kiribati showing changes in mean annual temperature, in extreme rainfall, and in terms of heat waves. Without additional efforts, each one of these will have consequences for health and higher burdens of disease that will be unequally distributed. It's mostly the poor populations who are affected the most. Next slide. The other two countries involved are Tuvalu and Vanuatu. I don't have specific data for either one, but graphically illustrates some of the challenges Jerry was talking about small atolls, narrow islands. I would like to make one comment about an earlier comment about how eventually sea level rise will inundate these islands. These islands are going to become uninhabitable before that. The coral atolls have freshwater lenses underneath. With sea level rise, with additional pressure on those freshwater lenses, there's been saltwater intrusion, which means these islands are losing their water. When they lose their drinking water, they're going to be uninhabitable long before they're going to be inundated. Next slide. Thank you.
Thanks, Dr. Ebi. And on that happy note, so Dr. Keener, are you there?
Yes, can you hear me?
Yeah. And I will just note that Lewis gave me an okay to run over on this panel since we switched some other things on here. So it's all yours, Dr. Keener.
Okay, I'm not seeing my slides now. They were there for a second and now they're gone. Oh, they're back. Okay, great. Thank you. So this is actually, I'll try and keep this short, make up some time, but it's a good progression on this panel with Jerry starting very globally and then going regionally, and then Chris kind of giving a overview of issues in the region. And really what I'm going to focus on is a specific project that we're working on with, involves climate change, human migration, and health in one of these countries, the Republic of the Marshall Islands. So I'm actually a research fellow at the East-West Center in Honolulu, Hawaii, but I'm also the lead PI of the Pacific RESA program, or the Regional Integrated Sciences and Assessments, which is a NOAA project. There are 10 or 11 teams now scattered throughout the United States that really focus on how to make climate information of all sorts useful for decision making. So while my background is in hydrology and climatology, we work very interdisciplinary on a bunch of different projects that are very regionally and sectorally based. So what you're seeing here is the U.S. Navy bringing portable reverse osmosis units to the Republic of the Marshall Islands a couple of years back when they were suffering from a drought. And that's just kind of to set the stage for something that happens very regularly in the Marshall Islands, which is, again, with those thin freshwater lenses, when drought hits and it hits for an extended period of time, they become vulnerable very quickly. And we see a lot of things that ricochet from those impacts. Next slide, please. So I couldn't see all of the slides before, but just in case people are wondering exactly where the Marshall Islands is, you may have seen this. There's a zoom in on the Pacific region for where the Marshall Islands is. It's a series of hundreds of coral atolls, again, in the Western Pacific. As it pertains for the United States and for governance, throughout the Pacific Islands region, there are a bunch of different governance systems that run throughout the region, but the Marshall Islands is a freely associated state of the United States. And what this means for them is that the COFA, or the Compact of Free Association, allows citizens of the Marshall Islands to live and work freely in the United States. They have a United States passport, but they're not citizens. They vote in the Marshall Islands for politicians in the Marshall Islands. And what does this mean for the United States? So in return, the United States gets access to the exclusive economic zones, which are those kind of jelly bean shaped bubbles around the islands. So those waters. And you may recognize in that zoom in, Kwajalein, which is a major military missile defense base on one of the atolls in the Marshall Islands. The other highlighted thing there is Majuro, which is the capital, which will be some of the focus of this talk. Also of interest, the Compact of Free Association is set to expire in 2023, at which point a lot of the other freely associated states and the Marshall Islands will be under option of either renewing that association with the U.S. or associating with another country potentially. Forward slide, please. So the next slide, you've already seen these. I just thought I'd throw one in case no one else showed what an atoll looks like. But this is really kind of just highlights the vulnerability and the reality of what living on a thin strip of land in the middle of the ocean looks like. Forward slide. So what I'm really going to talk about very quickly is just a project we're doing, which is looking at climate-induced migration in the Marshall Islands. So of course, human migration is a very multi-causal issue. But what we want to know is to what extent are climate stressors already driving human migration in the Marshall Islands? So with the Marshall Islands, you may have seen them represented in the New York Times and a lot of articles. They're really a poster child for both vulnerability and for global representation of islands at these UN conferences. The UNFCCC have really standing up for island rights and showing what the true impacts are on a lot of these places. So we wanted to know not only what extent climate stressors are driving human migration, what are the impacts in both source and destination areas. So not only the impacts from people from more rural islands moving to the capital of Majuro, but also people in the RMI moving freely to the United States to a couple different source destinations throughout the region. Why do those reasons vary among different populations in the RMI for migrating? The methods that we're using are interviews, household surveys, and mapping in 3 locations. So within the RMI, so in migration from outer atolls, and then migration to the states of Hawaii and Oregon, which are 2 of the most popular places for Marshallese citizens to go. And one of the reasons is because in Oregon, Compact of Free Association citizens actually qualify for healthcare in the state. So I'll get to the health connection in a minute. So some of those outputs will be maps of flows of the migrants and really looking statistically at explanatory models of the drivers of migration. Next slide. So how does this relate to health and drivers in the RMI? So one of the WHO reports that Kristie mentioned briefly was looking really at that country level, the connection between health and climate change in the Marshall Islands. So some of these concerns you already heard: diarrheal disease, malnutrition, vector-borne disease, mental health, respiratory diseases. They also see other things like conjunctivitis or pink eye when there's drought. And what you're seeing in the bottom there It actually looks very beautiful, like a tropical paradise, but those aren't giant swimming pools. Those are the sources of drinking water for the entire island of Madro. That's their, what they call it, the reef, the runway reef catchment. And so they collect all of the water as rain that falls on the airport runway and funnel it into those reservoirs, which are of course flanked by the ocean on either side. So when there's a drought and those reservoirs go down, that's when the island's really in trouble. Up in the right, I also wanted to point out the reality of atoll living. So that schedule that you see from Sunday to Saturday with the water hours, that's not when the office of the water and sewer company is open, and that is not that's not a drought condition. That's regular water service. So 4 days a week the taps are off. Sunday, Tuesday, Thursday, Saturday, there is no water service. So that's just regular life living in Madro from the public water supply. Next slide, please. So back to El Nino, I didn't see what Jerry actually showed from for the El Nino impacts, but I'm sure it wasn't this picture because I made it myself. But so what we're looking at here is really the impacts of El Nino specifically on food and water security within this region. So the Republic of the Marshall Islands is in the middle of this map, and you can see the El Nino impacts. This is the following months after it begins. So January to March of the following year of an El Nino, you see this dry patch extend from Hawaii all the way down to the southwest region. And that dry yellow blob is also associated with lower sea levels and increased tropical cyclone frequency in a lot of these areas. So it's really kind of a triple whammy of drought, storms, and these low sea levels. And again, this is what's driving climate variability in this region. These cause a lot of the more predictable impacts that we see. Next slide. But what we really want to get to, and what is interesting about this series of talks, I think, is that we want to get to how do we take those physical drivers and climate indicators that Jerry showed and really turn them into indices and thresholds that we can apply to observed both current and future impacts on people and ecosystems in different sectors. So in this case, we'd be looking at how do we take a climate variable, for example, a 3-month index of precipitation, and turn it into an indicator of human health, and then how do we link that to when we see a threshold of a policy response or an action on the ground. So what are these thresholds that we can identify to continue to assess and monitor and perhaps prepare better for some of these impacts? Next slide. And so really when it comes to the Marshall Islands, these are some quotes from the initial work that we've done on this migration, health and migration survey work. But really what we've found so far is that people are not reporting that they're migrating mainly because of climate reasons, but they are deciding not to return to the Marshall Islands because of climate change. So they're saying they left, climate change was initially not a factor, we moved for better education, but now I can't return. I'm terrified of living in the atolls when you hear the ocean pounding the reef. Or the last one, we can't farm local crops because the soil is not good. I know if I return to live close to the ocean, the sea will destroy my place. And again, some of that is salination of the soil. So like Kristie said, the atolls are going to be uninhabitable for a bunch of reasons before they're inundated by sea level rise. Next slide. And this is looking at, these are why people rated the most highly that they were migrating from the Marshall Islands. And as you can see, the top one on the top of this graph is seeking better healthcare is one of the main reasons Marshallese moved to U.S. So by far, that is a driving factor causing people to migrate. And that's for both themselves and their families. And so the last thing I want to talk about on this project before I talk about really some solutions, if you go forward one, is the immediacy of responding to these versus minimizing the long-term risks of climate and health. So when we've started talking to people at the epidemiological level, at the state epidemiological level in these ministries of health, a lot of times they're not interested in climate forecasts and learning how to use these seasonal or more longer term information when they can't even fund things that are burning fires on the ground now, like vector control. So if they're in the middle of a dengue outbreak and they can't even get funding for vector control, why are they going to care about these long-term climate risks? And then another thing that I think is interesting to think about is though the medical issues that climate migrants bring might not be caused directly by climate change. So for example, even though there might be somewhat of a link, diabetes or dengue, they are associated with a new population in these host communities. So we're seeing migrants come in from these places into Hawaii, for example, with new problems for the doctors in the communities that they're not used to dealing with. So really, how do we put policies in place that look forward for planning for the health needs of these migrants to these destination places? And if you go forward, one of the way we do that is by doing a lot of networking and partnerships and linking people together. So the Pacific RISA works with a bunch of different groups throughout Hawaii and the U.S. affiliated islands to really bring together groups of people and work on different things with this. One of the projects that we did that really focused on how to bring people together was a social network analysis. So if you go forward, we did a social network analysis of Hawaii and U.S. affiliated islands self-identified climate professionals. So SNA, or social network analysis, defines and visualizes social structures through nodes and ties between people. So really the ability to visualize these links is key. So social network analysis is usually used as a research tool, not a decision-making tool. So it's really looking at how information flows as opposed to how do I get this information from a specific person to a specific person. So what we really decided to do with this was do a novel thing and make it public. So you're actually using social network analysis to identify key people that you could then contact. Especially since professional turnover is very high in the Pacific Islands region. So having a list of people you can go through can be helpful. So if you go forward, we wanted to know, click 4, I think, or there we go. So can we identify the spatial and knowledge-related climate information gaps between climate professionals, link isolated sectors, create tools that increase connectedness within these different sectors and islands, and foster cooperation. So next slide, the way we did this was with a social network analysis survey. We had 331 people respond, the full network, and so how this works is it's a kind of a snowball sampling method, and people are able to list people who they work with if they're not on that network. So the full network actually consisted of 967 names, even though it was 331 people that answered. It was not confidential, so this was a very unique survey. We spent about 6 months contacting everyone listed to get their permission to be identified by name in the network maps. And all except 3 consented to being on there. And so this was really measuring the frequency of contact and create a preferential attachment network. Next slide. We disseminated the maps through emails, through our newsletter, and we created a web page on our website with all of the different maps. After we released it over the next 3 months, we got 641 page views on that. So it was, for us, that's a big deal. Forward, please. The results really showed that no sub-region was isolated, which we were glad to see. Hawaii professionals made up the majority, so 28% of the full network versus Palau making up only 5%, but they're equally central, so they're both talking to each other. The average path length between any 2 people was 3.25, so kind of playing the Kevin Bacon, connect 6 degrees of Kevin Bacon game. It takes about 3 people to get to any 2 people within this region. And we found that conservation and public sector policy were the most connected. So I'll just finish up with showing you quickly, if you go forward, what those tools look like on the website. You can go and look at the maps and the names within each place and each sector. So each map has corresponding tables of names and their measures of centrality. If you go forward one more, here's an example of, this is less useful. This is just visualizing what that whole network looked like. This is separating it by state. So the size of the bubbles indicates more connection, and the color indicates the state in this case. If you go forward one more, this is what it looks like when it's parsed by sector instead. So people who are working in public policy versus conservation versus marine biology or ocean science. If you go forward one more, lastly, this is just what it looks like in the Marshall Islands. So if you concentrate on the Marshall Islands in red and how they link to everyone else, they could click on this and look through the different people that are working in their region in different sectors. And if you're interested in looking at those in more detail, I know that was really fast. Last slide shows a link where you can go and download all this stuff. It's all available, and there's a publication. We're working on another one right now about this. And of course, I'm available for questions if anyone's interested. But hopefully that was interesting and brought it down to a more local example. Thank you.
Thanks. All right. Well, I want to thank our panel again, and I do appreciate everyone hanging in there. And if you do have questions, I think Jerry will be around, and David's obviously around. And if you do have questions for any of the other speakers, just let me know, and I can get those. So again, thanks to Chris and to Victoria, and enjoy that Honolulu weather, Victoria.
Thank you.
Bye-bye.